If you are new to our channel, subscribe, like, and don't forget to share. Okay, so first of all, Ampere's circuital law. Now let's say there is any arbitrary loop. It can have any shape. Okay, and in this arbitrary loop, different currents are entering and coming out. Okay, let's say these are the currents. Now, due to these currents, what will happen? The magnetic field will be developed on this loop. Let's select a point P. Okay. Now, according to Ampere, the magnetic field at point P, if it is suppose B, and here the length element is dl vector. So, the line integral of magnetic field over a closed loop is equal to product of permeability of free space and algebraic sum of electric current enclosed by the loop. Again I will repeat this. The magnetic field, the line integral of magnetic field over a closed loop is mu naught times of algebraic sum of electric current enclosed by the loop. This is Ampere's circuital law. Now in this Ampere's circuital law, students only they confuse in this case what will be the value of summation I. If I talk about, let's say this is I1 current, this is I2 current, and this is I3 current. So in this loop, if I say I1 current is entering and I1 current is coming out from the other side, so total sum must be 0 in every case, but it's not like that. Whenever you are taking the algebraic sum of current, always observe it from the top side. Okay, observe from the top. So I1 is outgoing, I2 is incoming, I3 is outgoing. So summation I for this special case will be I1 as positive, I2 as negative, and I3 as positive. The outgoing current you will always take positive, I1 and I3 outgoing positive, and I2 is incoming, we will take it as negative. I hope Ampere's circuital law is clear to everyone.
Yes, sir.
Yes, sir.
Very good. Now, applications of this Ampere circuital law. We are going to deal with the applications, and in applications, the first application is magnetic field due to a straight current carrying wire. Okay, first application. Magnetic field due to a straight long current carrying wire. So let's say there is a current carrying wire and the amount of current which is carried by this wire is I. Okay. Now due to this we want to calculate magnetic field at a certain point. So first of all what we will do, let's this is the point which is at a distance r. P is the point, distance perpendicular distance is r. Now to find the magnetic field at point P, we will imagine an Amperian path. Now the shape of Amperian path always we will choose by increasing the dimensions. So here if we increase the dimension it will become a cylinder, but we need only a portion of that, so it will be a circle. Okay. Now always when you are making Amperian path, Be very very careful, it is imaginary, so always make it with the dash line. Okay, this is Amperian path. Okay, now over here let's take length element dl, which will be tangential inwards. Now if we talk about the magnetic field at point P, right hand thumb rule says it is in the direction of dl inwards. So theta over here will be 0 degree. Now from Ampere's circuital law, we can write line integral of magnetic field along the closed loop is mu naught summation I. When we open this, it will give us Btdl cos 0 mu naught. Now summation I you can see from the top, if I say it is I only. B outside the integration, close integral dl cos 0 1 mu naught I. Now integration of dl is the length of this Amperian path, which is here 2 pi r. So B equals to mu naught I upon 2 pi r. Now this is a scalar form. In vector form, if I say, it will be mu naught I upon 2 pi r, and because it is inside, so minus k cap. So minus k cap will be there. Now if we plot the graph between magnetic field and the distance r, okay, it is inversely proportional, so definitely it is going to be rectangular hyperbola like this, be inversely proportional to r. I hope it is clear to everyone.
Yes, sir.
Right. Remember that sometime there is semi-infinitely long wire. So semi-infinitely long wire, we will keep the magnetic field just half of the complete wire. Okay, so it will be mu naught I upon 2 pi r and into 1 by 2. Okay, this is very very important. And one more point, if point P is on the wire itself, okay, let's say this is Q point, so magnetic field at the wire will be 0, and sometimes it is along the axis of wire also. Again, let's say this is R point, magnetic field along the axis of wire will be 0. These are few very very important points for the solving numericals. I hope it is clear to everyone. Okay, now the next application number 2, magnetic field. Magnetic field due to a solid wire of radius, let's say here A. Okay, remember that this question is asked in 3 marks, sometimes in 5 marks, like 3 plus 2 in board exams. So it's very very important. Okay, and it will cover all the parts like hollow wire, solid wire, thin wire. So only one application will give you 3 results, 3 different results. Now let's say a wire is there, solid wire, and it is a long wire. Remember that it is not for a finite length wire. Okay, it is for a long wire. Now let's say in this wire the I amount of current is passing, and there will be 3 different situations where we have to find the magnetic field. Let's say start from minus infinity to plus infinity, and the radius is given here, which is A. This is A. Okay. The total amount of current which is here is capital I. Now first point I will choose which is outside the wire, and let's say its distance is small r. So case 1 we will take r greater than A. It means outside the wire. Okay. Now again for this we will consider an Amperian path, which will be a circular path. Here we will take magnetic field. If current is vertically upwards in the wire, magnetic field will be inside the plane, and the length element dl parallel to magnetic field, so theta will be 0 here. Again from Ampere's circuital law. Okay, we can simply write here the line integral along the closed loop or Amperian path will be equal to mu naught summation I. Now if we open this, it will be Bdl cos 0 mu naught, and again summation I, here it will be I. Observe from the top again, B is constant, uniform, so out of the closed integral, now integration of dl will give us 2 pi r. So the first case is done. The magnetic field outside the shell is mu naught I upon 2 pi r. I hope the first part is clear to everyone. It is similar to the previous one.
Yes, sir.
Okay. Now second situation, when r is equal to a, it means on the surface. Okay, on the surface. Now on the surface, in above expression only we will write r equals to a. So it will give us the result b equals to mu naught I upon 2 pi a. Right? This is magnetic field on the surface of this solid wire. Now if we consider inside the wire, that will be the third case, which is different from the first case. R less than A, it means inside the wire. Now in this case, if it is inside, let's say this is the point where I want magnetic field, let's say it is P dash. So again we will take a Amperian loop, okay, and there we will take magnetic field dl as we have taken on P, theta will be 0 here, and let's say the radius here it is r inside. Again from the Amperian circuital law, closed line integral of magnetic field will be mu naught summation I. Now here the current will be different. Let's say I1 current is passing through it, because in the first case the cross sectional area, that is complete cross sectional area A, from that current is passing, that is I. Now here the cross sectional area will be less, so amount of current will be also less, that it is I1. So if we open this, it will be closed integral Bdl cos 0, then mu naught, and summation I, it will give us now I1. You see I have mentioned here, it is I1. Again magnetic field is uniform, constant, integration of dl cos 0 1 mu naught I1. So magnetic field here is mu naught I1, and integration of dl, that will be 2 pi r. Let's say this is third equation. Now over here I1 is unknown to us, and to calculate I1 we will use current density, concept of current density, which we have studied in current electricity. So current density will be I upon pi a square for the complete wire. Now for this Amperian path of radius small r inside the wire, we will say it is I1 upon pi r square. Now pi cancel. So I1 we are getting as I r square upon a square. Now substituting this value in the above expression. So magnetic field will be mu naught upon 2 pi r into I r square by a square. 1 r cancel, so it will be mu naught I r upon 2 pi a square. So this is the final result of magnetic field inside the solid wire. I hope it is clear to everyone.
Yes, sir.
Now the graph is also
Yes.
remaining. The graph part, let me draw somewhere here. Okay, so that it will be finished totally. If we talk about the magnetic field variation with the distance. Okay, so initially up to the surface, we can simply say B proportional to R. You can see the last formula here. B proportional to R. Okay. And beyond that, it is decreasing. Outside, it is inversely proportional. You can see the equation number 1. It is giving B inversely proportional to R. So it will decrease rapidly. So this will be the graph between distance and magnetic field.